CBAM, Convolutional Block Attention Module, is an extension of squeeze and excitation. So squeeze and excitation is this part of your neural network, which is going to pay attention across channels. You can have a similar architecture trying to pay attention to spatial points in your space. You take your input, you get your attention, you multiply, you take your spatial attention, multiply by the outcome of this operation here, and then you're going to get your refined features. Mathematically, you have your intermediate feature map, which is going to have some height, some width, some number of channels. This first attention module is exactly what you have for squeeze and excitation. You get a single vector, and then you're collapsing the height and the width. For 2D spatial attention, you're collapsing the channel. So there is a question in the chat. Is it the combination of attention across channels and attention across pixels? Exactly. So the previous one was squeeze and excitation, was about attention across channels. This one is attention across space. It's a combination of both. So you're right. What do? You get your input, F, you take your input again, you push it through your 1D channel attention module, whatever that is. I'm going to go into details. And then you just simply multiply them pointwise. You take the outcome, which is going to be F prime, you push it through your spatial attention module. I'm going to go into more details, mathematically, specifically what that is. And then you're going to pay attention to some pixels more and to some other pixels less. Let's focus on MC, the 1D attention. This is exactly what we have for squeeze and excitation with a little bit of modification. Previously, you were doing only average pooling across your pixels. Here, you're also doing max pooling. You push both of them through a multi-layer perceptron. You're going to get two outputs. You add them together, push them through a sigmoid, and then you're going to get your channel attention. Mathematically, you take F, you average pull it, you take F, you max pull it, push it through the same multi-layer perceptron, which is just you multiply by a weight and another weight. And then you take the outcome, push it through a sigmoid, and then that's going to give you your attention across channels. And then usually to save some computation, you first go into a lower dimension by W0. So you're reducing the number of channels first, and then you increase it. You go back to C. And R is the reduction rate. Spatial attention module, you take your channels, you take your feature maps, you max pull across the channels. Another time you average pull across the channels. You concatenate them, push them through convolution, sigmoid, that's going to give you a spatial attention. Mathematically, you max pull, average pull, you push that through 7x7 convolution, through a sigmoid, that's going to give you your attention. And then you concatenate them on top of each other. You take F, you get your attention, multiply, you get another attention over the space, multiply, add them, a shortcut connection. And that's your block. You keep repeating. How does it perform? You can compare with ResNet without any attentions, with squeeze and excitation, which is attention across channels. And this one is attention across both channels and space. And you're getting improvement across the board. How do you visualize this? You can visualize your attention, or there is another technique for visualization. This one I'm going to cover later on when we talk about visualization and understanding neural networks. But for now, take my word for it that you can actually visualize convolutions and where they are focusing. There's a technique for doing that. You have ResNet. It's going to be 80% sure that this is a frog. You're going to have ResNet plus squeeze and excitation. It's going to be 87% sure. Or you can have ResNet from CBAM in addition to CBAM. It's 96% sure. But then you can actually see what the neural network is looking at. So this one is looking at the frog and then some parts of the domain that don't really matter. Squeeze and excitation fixes that a little bit, but then it's missing the head. It's paying less attention to the head of the frog. CBAM fixes the entire thing. It's not yet perfect, but it's where the neural network is looking at. And then these sorts of analysis, these are cool plots, cool visualizations. We are going to do them later on. We're going to see the details of how you can do it. The sigma, the question is, what is the sigma in MC? There is also a sigma here. These are the This is exactly the sigmoid function. This is 1 over 1 plus exponential of negative x. So your sigma is exactly what you have here. Okay. So today we did a lot of attention, at least simplified version of it for images. Any questions about that? Okay, perfect.